Hi guys, Shouvik and welcome back to our YouTube channel. So let's jump on the today's question. Yeah, so today we have maximum candies allocate to K children. So now read it the question once. So what we have, you are given a zero index integer array. So we have a zero index integer array of candies. So on the questions they have provided a array of candies where each elements of the array denotes a pile of size of candies of I. So there you can consider like there are a list of candies they have given. Now each index of a particular candies there is a piles of candy. So if I am at index 0, so there you can see a piles of 5 candies are there at candies list of index 0. As simple as that. There is no super magics they have written here. Now you can divide each pile into any number of sub piles. Now here we have 5 candies, so you can divide these piles all together. So that is a pile of candies. We have five candies grouped in a one pile. Now you can divide this pile in a group of candies, group of sub piles. So you can divide it like this. Here it is five piles. You can divide it 2 comma 3. So then your resultant candies list can be 2 comma 3 comma 2. 5 is going to be divided into piles of candies 2 and piles of candies 3 and 8 comma 6 as it is. So you can do so. You can divide the number of, you can divide each pile to any number of sub piles as you want. What is the lowest piles you can divide? These 5. You can divide of piles of 1 candy 1 5 times, and then 8 kobe you can divide 1 like this 8 times 6 kobe. So that is the sub piles you can divide. But you cannot merge two piles together. But if you want to do like if you want to merge 5 and 8 to a single pile, then you can't do so. Then if you are telling me, hey Shouvik, let's merge two piles 5 and 8 and make a piles of candies 13. But no, on the question stated you are not allowed to do so. Okay, fine, let's move ahead. You are also given an integer k. They have also given an integer k. You should allocate piles of candies to k children such that each child get same number of candies. Now there are k children came to your house and you have the piles of candies to your own refrigerator. Now you have to divide same number of candies to the k children. Okay, fine. Sorry guys. Now you will ask, okay, we have candies of k, we have candies of piles, different piles. Now we have to divide to a k children. Okay, fine. And the constant is each should get same number of candies. Okay, I will take care of that also. Now, what next? Each child can be allocated candies from only one pile. So you can't do if children one has come to your house and you can say, hey children one, can you take piles 5 and 8 together? You can't do so. You have to allocate only one pile of candies, and some piles of candy may go unused. That can be unused because let's suppose there are lesser child arrives to your house and you have more candies piles. Then obviously you have some piles of unused candy which you can eat later on your free time. Right. So now we have to return the maximum number of candies each child can get. Now you have to be a little bit greedy. You on the mind of contributions to the child to make them much more happy. How you can do so? You can allocate maximum number of candies to each of the child. So let's suppose initially we have 5, 8 and 6. So our tendency on your greedy mindset, can we allocate at max 8 candies? Like can we allocate 8 candies to 3 children? Our tendency should be something like this, like maximum number of candies we can allocate to each child. Can we allocate all together 8 candies of piles to every child? Our mentality should be like this way. But if you are not allocated to do so, then we will figure out how we can do so. Then we will increase to allocate that 8 number of candies to some lesser number of candies. That we will definitely try for sure. But our mentality should be like this. Yeah, like for this question you can see, but you can't merge two piles. You can divide a piles to any number of sub piles, but you can't merge. So like if you can state me like, Shouvik, I am a little bit greedy kind of mindset. Let's suppose there are two children arrived to my house and I have a piles of 6 and I have a piles of 8, I have a piles of 5. So I want to give them like, yeah, 8 piles only, and I have 5 piles here, 6 piles here. Why can't we merge those 2 piles and make a piles of what? 5 plus 6 is 11 piles, and so I have a resultant piles of 1 8 size piles and another 11 size piles, and 1 11 size piles. You can, now you have two children in your house, you can give 8 piles first child, another 8 piles of candy from out of 11 piles of candy to the second child, and now that way you are able to maximum number of candies distributed to the two children. But on the question stated, you can't merge two piles of candy. So 5 plus 6 merging is not possible. You can divide it, but merging is altogether not possible. Now let's understand the first test case. Now they have stated we can divide candies 1. So candies 1 is a candies of pile size of 8. This one is the candies 1, that is 0 indexed, they have written, into two piles of 5 and 3. So 8 ko we have divided 5 and 3. And candies 2 you have divided into two piles of size 5 and 1. So what we have in candies 2, we have 6 candies. Now you have divided two piles of size 5 and 1. We now have 5 piles of candies after divisions. One is this 5, 8 ko we have divided 5 and 3, 6 ko we have divided 5 and 1, 5 and 1. So we have total 5 piles of candy, and we can allocate the 3 piles of size 5 to 3 children. Now here you can see what is the maximum pile size we have, 5, 5, 5. And do we have any pile size which is maximum and altogether have k occurrences, because we have to divide to k children and all children should get same number of candies. Each children should get same number of candies. So yeah, we are able to do so. We have five candies, 5 maximum pile size candy with 3 occurrences, and we have to divide among the 3 children. So we are do so. So we can allocate 3 piles of size 5 to 3 children, and it can be proven that each child cannot receive more than 5 candies. So our answer on that case is 5. So each children got maximum 5 candies on that allocations. Now here you can see, and we have returned a 0. Why so? Why so? We have candies of size 2 plus 5, that is 11. 2 plus 5 is 11. Sorry, 2 plus 5 is 7. 2 plus 5 is 7. And you can see there are 11 children altogether arise to your house. And you have a constant of each children should each children, like every children should get same number of candies. Each children should get same number of candies. Now you can think of very intuitively, like if I have 7 candies and if 11 children arise to my house, if I allocate one candies to everyone, then also I have like I have some shortage of 4 candies, right? Because 11 minus 7, that is 4 candies, still I have shortage. So there can be 4 child which is going to be taking off 0 candies from me because I have left out of candies, right? So on that case, but you have the constant, you have to allocate same number of candies to each child. You can't do like, hey, first 7 childs you can take a candies of 1 and next 4 I will say goodbye. That I can't do. I have to either allocate one child to all the 11 members, or I have to do make them all of them unhappy on this case. So we make them all of them unhappy as per to make the question constant in hand, and we are allocating no candies to anyone. I think question is now you guys got the entire grip of the question. This question understanding is altogether a little bit tricky, so I explained on like very granular levels. I think now you got the questions altogether. Now let's move on the solution. Now there are two things, two approaches. One is a very brute force. Now what you can do, you can, what is the maximum candies? What is the maximum candies you can assign to a particular child? What is the maximum candies? It's 8, right? What is the maximum? What is the maximum of candies piles we have? That is the maximum candies we can assign to a particular child, and that can be my very maximum case possible answer, right? That is can be very maximum possible answer, because we can't able to merge. So if I not able to merge, then our answer is the maximum of candies at very max case, and but we are allowed to divide. And if we are allowed to divide, then our answer should be on the lower side. But what is the maximum answer possible? Our maximum answer possible in this case is 8 altogether. What is the maximum candies we can assign to one child, right? And what is the minimum candies we can assign to a one child? That can be of 0 altogether, because on that case we make all of them unhappy by not assigning to any child any candies to any of them, right? Exactly. So now you can do on the brute force, you can iterate over the candies list, and you can, let's suppose you have think. So let's jump on our OneNote. Let me check if I have this enable. Otherwise, let me connect. Where we are, where my space picks all together. Connected. We are on screen of OneNote. Okay. So what I can think of ki, hey, this is the start. Okay. So what we have, let's suppose we have 3, 7, 9, 15. Like this way we have dot 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 dot, we have candies. Now what we can do, we have defined our range, our answer range can be, we can allocate no candies to any of them, and it can go at max, very max case, maximum of candies, sorry, it can go at very maximum of candies, right, very clear and straightforward, so we can start iterating for one for loop, allocation, and we can start it from 0 to 0 to max of candies, we can do so, यार क्या होता है इसको, now within this we will start another for loop for I, that should be start from your candies list from 0 to, I should start from your candies list 0 to n, and what 0 to n, and what you can do, so you can try to, like, now with these allocations, can you make all the childs with this allocation, what allocations, with these allocation variables, can we make everyone to be happy, like k children that has arise to your home place, can you make everyone to be happy, how you can check so, you can take a, like, satisfy, now total satisfy, you have start with 0, now you can do, now for candies of I, how many, what you are trying, to allocate every children, to allocate number of candies, allocate is now altogether going from 0 to max of candies, how many candies you are going to, on this particular loop, how many candies you are trying to assign to each child, it is allocation variables. So now if you, how many, now on this case, how, with this candies of I, so candies of I is the piles of candies you have of a index, let's suppose 0 or 1 or 2, whatever the I value is, so you have that many candies in your hand. Now with these candies, how many child you can satisfy, with each child, allocation number of candies will be taking from you, that is should be candies of I divided by allocation. So that many child you can satisfy with these piles of candy at max. Why divide? Because you can divide your piles to sub piles, that is allowed. So let's suppose if I move ahead, so if you have 13 piles of size 13, and if you allocate each child with candies of size 5, how many subpiles you can divide? You can do 13 divided by 5, that is bring out to be, that is of, for sure, are integer divisions, that is an integer division. It is giving you 5 2s are 13 and dot something, but it is giving you 2 only, because that is an integer divisions, you will get 2. So you can make 2 child happy with this piles of size 13. You have assigned 5 and 5, and you have left with 13, which is actually the unused, you can eat on your own later. That you can do. But this actually going to be, childs are going to be taken this, how many childs are taking this? 5 and 5. So 2 childs we are going to satisfy. How we derived it? From candies of I divided by how many allocations we are doing on this particular iteration, that is divided by allocations. Okay, very good. So now with this candies I, we are able, our total satisfactory plus equals to how many, plus equals to how many satisfactory childs we are able to generate on this particular go. Very clear, right? Very clear. Now this way we are keep on generating. Now if at any point of time my total satisfactory child is going to be greater than or equals to k, because there are k child altogether arise to my home place, so I can say with this allocation, whatever the allocation list we are iterating, with these allocations we are able to make what we are able to make, we are able to satisfy k children. So we can break our loop from here, and our answer is going to be updated with these allocations, because with these allocations we are able we are able to do so. We are able to make all k childs. Okay, that is going to be a little bit hazy. That is the below part what we have done for understanding, and till this, that is the pseudocode of ours, right? So we have break it out from all together here. Now, what is the time complexity of this approach? That is the very brute. And again you will try for higher value of I, because you are iterating from zeros to max candies. Again, your allocation is going to be first is, let's suppose 2, then you are trying for allocations with 3. Like this way, you are keep on trying. And at the first points where we are not able to allocate with a particular allocations, you are not able to make all the child happy. You can say like after that, what is the allocations value? After that, what is the allocations value? You are not able to do so. Now, can you imagine these things on your mind? Let's suppose you have a particular point here with this allocation, you are able to make k child k or greater than equals to k child happy, but for, let's suppose, this index, with this index you are not able to make k child happy. This index fine, but with this index you are not able to do so. So do you think of taking this index, are you able to make childs altogether happy? Are you able to make more allocations by allocating more candies? Because let's suppose here we are trying to allocate as much candies to individual childs which is out of stock for us, so taking more candies, if we are trying to allocate more candies, so that is a monotonic increasing sequence. This allocations is a monotonic increasing. We have start with from 0 to n, 0 to max of candies, and with this particular allocations we are not able to satisfy that child. Do we think like allocating more candies to individual, if we are not able to do on this particular index, do you think if we are trying to allocate candies with more allocations to individual child, do we able to do so? Exactly not. Because maybe here you are out of stock, or the piles you have, the piles altogether not winding out to the feasibility of you are able to allocate that many candies to individual child. So how you can, let's suppose on these particular points you are altogether out of stock, how you can do to take more allocations to make it in stock? That is completely not possible. And with lesser allocation, can we say you should be always be in stock? So now you can exactly match the today's question with just yesterday's question we have solved. If you not watch it, please watch it, because we have detailedly explains how binary search on answer is going to be work on this type of question, how binary search is work. I have actually provided you the feel how binary search on answer is actually work on the last of our video. But yeah, I have also given you like mostly the feelings of how actually binary search is working on answer list. If you have the answer boundary, so how you can figure out your answer by a binary search to pinpoint what is the exact answer of our case. So now I think you have a monotonous sequence. So now we have a monotonous sequence. So standing at a particular index, answer can be valid. Just after that index, answer can be if answer has started invalid, then from this particular index to very last, that is altogether a chunk of invalidity. And if you have just last point where your answer is valid, then altogether it's left. You can say this is a point chunk of validity. This is the chunk of valid window. And this is the chunk of invalid window. So considering this particular point of validity, towards its left all are valid. Towards its right, where the first invalidity has started occur, considering that all are invalid. So we have a monotonous sequence. And if we have a monotonous sequence, then can we think of a binary search? We should. I think I have give you the entire explanations. Now jump on the question solutions altogether. There I can explain you on the code perspective. So now we have to do a binary search on answer kind of things. We have a possible answer segments where the answer can be lie. So we have initialized our answer is 0, so that means we are not able to, we are all together at the very starting of stock. We are in out of stock actually. So let's suppose we brought two candies and there are altogether three childs as next day came to our house. So that is we are not altogether satisfy any of them. We have to like say bye bye with zero candies to all of them, because the constraint is we can't make two of them happy and one should go unhappy. That is not a case. So we have start our answer with 0. And let's suppose we are at our left and right boundary left, let's suppose we are trying to make at least one candies to every child who has arrived to our door. And what is the maximum candies we can assign to a particular child, particular answer? So we know, we have already discussed, that is our max of candies, that is the maximum possible of answer is possible. So let's suppose how it is. What is the test case on that case? Let's suppose you have candies given as 5 5 5 and there are exactly k equals to 3 child has occurred. So what is the max of them? Max is 5. Max is 5. So you are able to give 5 child, first child can take this 5, second this, second third this, like this. So our maximum possible valid answers can be max of candies at max. But yeah, if it is not possible, then binary search is do. Binary search will be going to do in our behalf what it is the best divisions it can possible. So mid is going to be left plus right by 2, same template that I am following I think last 2 to 3 videos when they have started giving the binary search questions. So mid is going to be left plus right by 1, and is possible functions is going to be the brain of the entire binary search that we all know. That is the standard template I am following last 1 to 2 videos. Please try to make this template to your head. That is the standard binary search template. On binary search on answer to for sure. Now is possible is actually the hard code of this code logic of this particular solutions. If is possible, like with these allocations we are able to make k children's happy, satisfy the k children's, then we can assign answer to be this particular mid. Okay, this particular mid you are able to do so. Now let's try to do with higher value of mid. So this means you can do. Now our question clearly stated, can we do maximum number? What is the maximum number of candies you can assign? So this assignment is a valid assignment. Now Shouvik, can you assign more candies with the piles that you have it in your hand? Can you assign more candies to the child? So this is something like, let's suppose your initial mid is pointed to here, your mid. Now with this, if you make it valid, you make it valid. So this is the valid for sure, and left window we know is altogether valid. Can we make something more higher allocations to make more child happy, to make more some child happy? So that's the reasons. Whatever the L pointer, hey L pointer, can you shift yourself to mid plus 1? Can you do so? L said yes, definitely I will do. So L is going to be shift to L equals to mid plus 1. And if that is not a case, that is something like if your answer is lying something a point of invalidity here, if your mid is here, then okay, till right, so there is no chance of getting answer. Can you try to get it some lesser place? There may be lesser allocations we are able to make k child happy. So your right pointer, which is standing at here initially, can you make your right pointer to point here? Your right pointer, then on that case, mid minus 1. Correct. As simple as that. So your mid pointer is going to be, right pointer is going to be mid minus 1. Now let's understand is possible. I think I already give you the test how is possible functions is going to be work for our case. So is possible functions is going to be take allocations. Now you remembered mostly this brute approach. So on this brute approach, the time complexity of this brute approach, we are going to iterate all together some kind of standard iterations, allocations from 0 to maximum allocations. And this is kind of a linear time complexity, so I written as n, and here too you can see for sure you are iterating n. So that is of n square time complexity, and as per the constant, also I didn't see the constant altogether because binary search altogether hit the very first to my brain after seeing the question. So yeah, it is of 10 to the power 5. So 10 to the power 5 into 10 to the power 5, that is going to be a very bad things. We are not writing that kind of solutions, so for sure. Now what we can do, so we have proved this allocations is a monotonous sequence. We have proved it below. So we have proved it how this allocation sequence is a monotonous sequence. Now if we have a monotonous sequence, then we have just did non-linear iterations, not do linear iterations of our allocations. Can we do a binary search based iterations on this allocations list rather than doing a straight iterations, linear iterations on allocations? We are trying to make a binary search based iterations on this allocations list. Yeah, we just did the same things, and inside this I think we have mostly write the exact same code itself. We have allocations list, so we have make it as a binary search based approach here. So that can be our mid is actually the allocation, like each child, what is the maximum candies we can assign to each child. So that is the each basically said what is the maximum allocations we can give to a individual child. Yeah, and then I think that we have also discussed like total satisfactory child. Initially we have start with 0 and we have iterating from I from 0 to n, and we are trying to satisfy how many child with this candies I with each value with that is your allocation iterator on the one note we have discussed. What is the maximum what is the maximum child you can satisfy with this? So that is of candies of I divided by each. So that is the number of child you can satisfy. That is the number of child you can satisfy with this particular candies file taking. Now we are just adding it to our satisfy child. So total satisfy child is going to be satisfy child, and if any point of time if our total satisfy child is more than equals to k, if it is more than equals to k, we are able to make k or greater than k child happy, then we are good to return a true. Yeah, we are able to with this particular allocations, we are possible, it is very much possible to allocate make k child happy, we are returning true. But if this entire for loop executed and we are not able to make k child happy altogether, then we are returning a false, very straightforward false after that iterations. So please remember, like each possible functions, if you are able to write each possible functions in a binary search on answer based question, then your 90 to 95% job is altogether done. And if you and this another 5%, you are altogether identifying it is a binary search on answer question. So your 5% is you are identifying it is a binary search on answer, and your 90 to 95% is how you are basically writing your each possible functions. If you able to write your each possible functions in a very like linear time complexity, because all you make your brain something like this, your binary search is altogether adding a log n for sure, and your each possible functions definitely need to add a time of big O of n to your time complexity. Then only that is going to be accepted, right? Now, yeah, that's all about like today's question. I think you guys got the entire gist of the question. Now, I think time complexity is very trivial. You guys already got it. So the time complexity, but yeah, like for sake of simplicity, I am going to mention it because maybe someone is not able to catch it up on the first go. So this binary search, we are doing max of candies. What is the candies of I? It can be of 10 to the power 7. So that means of max of, so I'm writing it as a n. So you guys got it, right? We are binary search of 10 to the power 7. I will write the mathematical versions of it also. So there I will write. And here we are basically doing a standard iterations of candies length, which is of size n altogether. So here you can say it is a kind of n log n time complexity, and that is the best time complexity we can achieve by this. And yeah, and this is on the mathematical term something like of your n is what? N is something like of 10 to the power 5, and n is something like of 10 raised to the power 5. And what binary search you are doing of log of 10 raised to the power 7, 10 raised to the power 7. Yeah, that is your like final time complexity. You can put it in, so log base is always 2 because we are operating with binary only in mathematics, in computer terms. And on space perspective, you can put it in any online calculator and you can calculate the time, exact times how it is going to be taken. It should be like very low, you know, because some log factors is going to be very low. Now on space complexity, you can say, do we think guys we are using any extra space? No, right? Everything we are using in terms of variables only. Everything we are using in terms of variables only. So you can say the space complexity is big of 1 altogether, right? So that is the most optimal solutions for this particular questions, I have to say. Cool. Okay, so if you guys understood till this point, please do subscribe to our channel and please turn on the notifications so that when we are going to upload any latest video, you will get the quicker notifications and you can jump on the videos. But yeah, please try to solve this question to your own to get a better grip on this particular topic on binary search and answer. Okay, so bye for today. Happy Holi to all of you guys. Bye bye. Meet you tomorrow.